Hello, my name is Jared Skeens and welcome to the Zoom room. Today we want to look at Pure Math 3 integration part 3, and we're going to look at a method called integration by parts. So first thing I want to do is explain where this integration by parts comes from. And it comes from the product rule from the derivative. So if you remember the product rule from the derivative, you take the derivative of a product, u times v, you get 1d2 plus 2d1, u dv plus v du. Now, if we're to rearrange this for the u dv, we get u dv equals the derivative of uv minus v du. And you say, why do we want to do this? Well, remember, integration is just working backwards from the derivative, or actually, if you're doing that, it's called the antiderivative. So if we integrate this, now that we have this differential here, if we want that differential to go away, to do the opposite, we integrate it. So the integral of u dv, if we want to integrate this u dv, it will equal u times v minus, because the integral canceled out the derivative. So here you have your d dx, and if you put the integral on that d dx, those are opposites, so it makes that cancel out, minus the integral of v du. So the integral of u dv equals u times v minus the integral of v du. This formula is in your formula sheet, but you should have this process down so that you don't really have to look at it, but it is there if you need to. So what we're going to do then is we're going to identify the parts, the u, the v, the du, and the dv. Those are the four parts that make up this equation, u, v, du, and dv. And once we've identified the parts, then we can put it together with this formula. And the goal is to take something that is complicated, that we can't integrate directly using our basic rules, and it breaks it up a little bit into these parts so that the integral of this end one here is a more simple integration that we can do. Therefore, we're able to get the complete answer. So this is what we're going to follow, and I'll walk you through that in a minute. And don't forget our three-step process here: simplify, integrate, and evaluate. This is just like a general guideline that you should be thinking anytime you're doing integration problems. Simplifying means, what do you have to do to get it ready to be integrated? Then the integrate is going to be the method of integration that you use, whether it's your basic math rule, u substitution like we saw in the last video, integration by parts, or whether you might have to do something else. And so that's the integrate, and then of course the evaluate at the end. So don't forget your kind of little mental roadmap there. So let's get started here and look at examples so that I can show you how this integration by parts works. So let's go to our first one here. And here you can see this is from Summer 18, paper 32, number 8. Here you see this diagram with the shaded region here. And it says the diagram shows the curve y equals x plus 1 times e to the negative 1/3 x, and m is the maximum point. And for part I here, it says find the x coordinate of m. Now we already did this back in the derivatives unit. Remember, the derivative allows you to find these stationary points. So I'm not going to do this again right now, but you can go back if you want to and look at the derivatives videos to study more about that. But what we're working on is this part here. Find the area of the shaded region enclosed by the curve and the axes, giving your answer in terms of E. So the key word here is find the area. Remember, as derivative application is slope, integral application is area. And we need to find it of this shaded region. We already know the equation of the curve. We can tell that the y-axis is here at the origin. Now what we need to find is, before we can integrate, we need to find this coordinate right here of where the curve intersects the x-axis. So let's go back to the board. Here we see our curve. Now, we want to find where it crosses the x-axis. The x-axis is the same as the equation y equals 0. So we're going to solve or set our curve formula equal to 0, meaning y equals 0, to find out where it crosses the x-axis. Now, at first, it might look a little intimidating, but actually it's not. Remember, it's already factored. It's already in a factored form. So you set each factor equal to 0. And exponentials cannot equal 0. Remember, that's one of the restrictions placed on exponentials. So this one you don't have to worry about. The only one that you're really working with is the x plus 1. So x plus 1 equals 0, and you solve it and you get x equals -1. So that was a lot easier than what it looked. And that just means our bounds of integration are from -1 to 0. Remember, you put the smaller one on the bottom and the larger one on top. It says find the area. That's our clue that this is an integration type question. So we found our bounds of integration. That's pretty much all we have to do for the simplify part. There's no rearranging that we need to do. And now we need to choose our method of integrating. And we saw before, you have basic math rules, and obviously you don't have anything in your basic math rules that follow this. You have use substitution, where they give you a substitution value to plug in. And in this case, what is the clue for us is that this is a product. If you have a product or a quotient of unlike terms, like here algebraic with exponential, or exponential with trig, or logarithmic with trig, or algebra with logarithmic. If you have product or quotient of these unlike terms, then you're going to use integration by parts. Now, it's very important as you set it up that you think about how you want to set up the parts. You're going to have 4 parts. Remember, we talked about U and dV. So that's what I put on the top level here. I put it in kind of like this box form with U and the dV on top. That's what we're going to integrate here. And then below that, we find the other parts. So from the U, we can find the du, and from the dv, we can find the v. So from u to du is derivative, and from dv to v is integral. So you're using both derivatives and integrals here, so you really have to be careful with your mechanics, make sure you're going in the right direction. And that is, so here you see the u's and the du, you see the v, and you also see the dv's. Those are the 4 parts. So that's just what it means by integrating by parts. Now we need to choose which of these terms is going to be the u and which one is going to be the dv. So is it going to be the x plus 1 as the u, or is it going to be e to the negative 1/3 x as the u? And which one also is going to be the dv? Now, what you want to think of is this. As you move from this top to the bottom, the one that when you take the derivative if it simplifies, if it reduces, that's the one that you're going to want to put for the u. The one that tends to go circular or not really simplify, that's the one you're going to put for the dv. So let's think about this. If you have an e to the x and you derive e to the x, you still get e to the x. It didn't simplify. In fact, it's just kind of going in circles. So we don't want the e to the x to be the u because it doesn't simplify when you derive it. So we're going to put it on the dv part. And if you think of the x plus 1, you put it here with the u. And when you derive it, it just becomes 1 dx. So the x actually cancels out and it reduces, so there's no x anymore. That's what you're looking for when you set up the integration by parts. The one that simplifies, you put with the u and derive it and it reduces. And the other part, like even a trig function, sine becomes cosine, cosine goes back to negative sine. You know, those ones that kind of go circular, you want to put on the dv part. Okay, so let's see how this works. So we have u equals the x plus 1. So we find the du and we just get dx. We can see that it reduced. That's good. Our dv is the e to the negative 1/3 x dx. By the way, the dx was not up here in our original equation. You do need to add it. Integrals undo differentials. You need to put it. It's an important part of the by parts thing. You want to be able to follow it through correctly. So don't forget your differential. You are free to add it when you set it up as an integral like this, even though it wasn't up here. So please add it in and keep track of it because you're going to integrate that and then it will go away down here. Now, this tends to be the part with that's a little tricky because you're integrating it, meaning you're going backwards. And so remember that e to the x is still e to the x, and then you divide by the derivative of this exponential up here. So of the exponent. So the derivative of a negative 1/3 x is a negative 1/3. You're going to divide by a negative 1/3. And when you divide by a fraction, you invert and multiply, it becomes negative 3. So actually what you did was divide by the negative 1/3 and it becomes the negative 3 like that. What I always like to do, especially in this area here where it's so easy to get mixed up between the derivative and integral, which way you're going, is just work it backwards. Doing derivatives is always easier. The derivative of e to the x is e to the x. The derivative of a negative 1/3 x is a negative 1/3. And when you multiply negative 1/3 times negative 3, you get back to 1. So don't just integrate it, but derive it again just to make sure that this part here is correct. You really want to make sure this is correct because this is your building blocks for the formula. So if you get something wrong in here, it's going to carry out through your formula. So be really careful right there. So let's follow the rule. Again, it's in your formula sheet if you need it. But again, it's a little better if you derive it in your mind from the product rule. That way you understand it a little better. So you get uv, u times v. So here's a negative 3 times x plus 1 times the e to the negative 1/3 x. Now, even though it looks complicated, you don't have to worry about it anymore because the integral canceled out with this derivative up here. So there's no integral on it anymore. It's ready to go. Minus, and there's a minus here, okay? I know it's plus, but there's a minus here, minus the integral of v du. Well, notice this negative here is going to change this negative out here into positive. So we got v times du, and the negative comes outside the integral and makes this positive. It's still from -1 to 0. The bounds of integration don't change. And then we have our 3e to the -1/3 x and the dx from over here. Again, don't forget the differentials. Then all we need to do now is integrate this. Notice it is not a product anymore. The product is what made it complicated. Now it is reduced. That x disappeared. We no longer have a product in here. So we can just integrate it directly. You are going to have to pay close attention to that because there are times that you'll see later where you have to integrate by parts twice. In other words, maybe you start with an x square, it reduces to an x, so you still end up with a product. You got to integrate by parts a second time in order to make this work. So there's no product here, so we're good to go. This part just carries down because it's already integrated. Now we have to integrate this part. So again, e to the x becomes e to the x. Just like over here, we divide by a -1/3, which inverts and multiplies to a -3 times 3 is a -9. So we get a -9 e to the -1/3 x. Now we have integrated it. That was this second step here. We did all of the integration method. Now we need to evaluate it from 0 to -1, or actually -1 to 0. You do top minus bottom. So when you plug in a 0 up here, so e to the 0 is just 1. You plug in a 0 here, you get +1. So be careful, when you plug in a 0, it doesn't mean it automatically cancels everything out. So you get a 1 times a -3 is -3. You put a 0 in here, and e to the 0 is 1 times -9 is -9. So plugging in the 0 gives us a total of -12. Top minus bottom, so minus, plug in a -1 here. Now we get a product of 0, so that wipes out this whole thing and makes it 0. Plug in a -1 here, and it makes it e to the +1/3 times our -9. Don't forget to distribute here this negative in front of the parentheses. Make sure you put that in parentheses, top minus the bottom. So you distribute the negative, which ends up making it a +9 e to the 1/3. Normally we like to write the positive term first. So 9e to the 1/3 minus 12. This is the area in terms of e, meaning no decimals, so don't use your calculator for that. And this is our answer. So there's our first integration by using the method integrating by parts. And we'll go through a couple more examples to make sure that you know what it is you're looking for and how to identify it. Okay, let's look at our second problem here. Comes from Winter 18, paper 32, number 3. Find the integral of ln x over x cubed dx. Then it says, hence, show that the same integral, now with bounds of integration from 1 to 2, equals 1/16 times 3 minus ln 4. So let's start with this first part here. Go back to the board. So what we're looking for is it says find the integral. Well, obviously we know we're integrating because it uses the symbol. And what we're looking for here when we try to decide what method to use to integrate, again, we notice that there is the quotient going on here. Remember, if it's a product or quotient, especially of unlike algebraic terms. So here we have this logarithmic term divided by an algebraic term. So that's our clue that we should do integration by parts. Now, if you noticed in the last example, the x was the one that we put in for the u. And yes, the x would reduce, your x cubed would become 3x squared. But if you're going at that rate, you would have to integrate several times to get it to go from x cubed down to x squared. That would be one integration, then down to x, and then to get rid of the x. That's a lot of work. So you want to consider your options. In this case, if you put the ln as your u, then when you integrate it, it becomes algebraic. And that's nice because instead of having unlike terms, they're both algebraic and they can combine, and it makes it easier to integrate. So in this case, so you really do need to take a minute and think through your options. Usually you want the one that reduces, but because it's a long way from x cubed down to just dx, you start with the ln x, it changes to algebraic. That means the x cubed, remember it's in the denominator, so it's actually x to the negative 3 dx is our dv. Remember we're using u dv here. So here's our u, is the ln x, and then the x to the negative 3 dx, that's the dv. So the derivative of ln x is 1 over x dx, and the integral of x to the negative 3, add 1, which makes negative 2. You divide by negative 2, so that gives you a negative 1/2 x to the negative 2. So there's our parts. Now we just plug it into our formula here, u times v, and it gives us a negative 1 over 2x squared. That x to the negative 2 drops below the division bar there. So a negative 1 over 2x squared times ln x. Now we don't worry about that product because the integral sign is gone. Remember, it canceled out with the differentials here. And so this product is okay, it's good to go. And now we have this part right here that we need to integrate. We have our negative 1/2 x, negative 2 ln x plus, that was the uv here. I left the x to the negative 2 upstairs for the right now, but you can bring it down. Minus, don't forget this is a minus, that's by the formula, the integral of v du. But because it's times a negative, this becomes positive. So we have 1/2. And now you have an x to the negative 1 times an x to the negative 2 is x to the negative 3. So be careful with these. This one is in fraction form. This one is in exponential exponent form. So be careful that you don't accidentally cancel that out the wrong way. So this is an x to the negative 1 times x to the negative 2 is x to the negative 3. So again, double check your mechanics on that. This really needs to be accurate if you're going to succeed at the carrying out of the formula. Now, again, this first part, just move the negative exponent down, and we need to integrate. Now notice, because algebra combined, this is easier to do. So again, you add 1, you get the negative 2, which I've already put down in the denominator. Divide by negative 2 gives you a negative 1/4. And because for part 1, we don't have bounds of integration, we put plus c. So don't forget the plus c, and this is the integral as far as we can take it. Then in part 2, basically has you do the same thing, but just carry on with the evaluate part. So we did the simplify. There really wasn't anything on this particular one to simplify. We were able to go right into the integration, and now we're doing the evaluate. So when we go to evaluate, we now have bounds of integration, so we don't need that plus c. Don't worry about the plus c because they gave you the bounds of integration, so the plus c goes away. Put in the 2 first, and notice 2 squared is 4 times 2 is 8. So we get a negative 1/8 ln 2 minus 2 squared is 4 times 4 is 16, a 1/16, and then top minus bottom. So here's the minus. Plug in a 1. Hopefully you recognize right away that ln 1 is 0. That's something you should be able to recognize. So 0 times anything is just 0. Plug in a 1 here and you just get minus 1/4. When you take a negative 1/16 plus, don't forget to distribute your negative. A negative 1/16 plus 1/4 gives you 3/16, positive 3/16 minus this 1/8 ln 2. And then we want to divide out this 1/16 to the front so that this is left with a 3 minus, and then when you take out the 16 here, you're left with 2 on top, 2 ln 2. And then remember your coefficient of your logarithm using your third law of logarithms. This can move up as the exponent and then become 1/16 times 3 minus ln 4, which is what the form it asked us to get it in. So this one was basically same thing, except this time we had a quotient instead of a product. We had to kind of rethink how we're going to do our parts, and then the rest of it from there was, normal, integrate, and evaluate. So let me set up another question for us. Okay, for our next problem, we get into some trigonometry here. It says, show, and this is from summer 19, paper 33, number 2, show that the integral from 0 to pi fourths. Now, remember, if you use your calculator for some reason, make sure you're in radian mode because we're now using radians here. And it's important with trigonometry, although you should be able to do this without your calculator. But the integral from 0 to pi fourths of x squared times cosine 2x dx equals 1/32 times pi squared minus 8. And this is a show problem. Notice it's worth 5 points. And again, just to remind you, my ratio is 5 to 7. In other words, 5 points of Cambridge question, Cambridge 5 points, is approximately 7 minutes of time for you to solve the problem. So you've got 7 minutes. So take your time. Let's go back to the board and look at what we got. So here's what they want us to show. They want us to show that this integral comes out to this conclusion. Well, what we notice right away is there's really nothing to simplify here. We've got our bounds of integration, and we don't have anything that really we need to change on it. But we notice that it is a product. So we can basically skip the simplify because there's nothing really to do to it. It's already ready to be integrated. But for our choice of integration method, it's a product of unlike terms here. We've got algebraic with trigonometric. So we're going to want to use our integration by parts. Again, remember the goal is to get something to reduce. So the algebra one will reduce from x squared to 2x. The trig one does not reduce. When you deal with trigonometry and derivatives and integrals, especially with sine and cosine, they just go back and forth. So the derivative of sine is cosine, the derivative of cosine is a negative sine, and the cycle goes on. So if you have something that's cyclical like that, you're going to want to put it in the dv part. And so our u equals x squared, so du equals a 2x dx. The dv is the cosine 2x. So the integral of cosine is sine 2x. Don't forget to divide by the derivative of the argument. So we have to divide by 2. Double check it by thinking it backwards. The derivative of sine is cosine, and then the derivative of the argument is 2. 2 times 1/2 is back to 1. So always just double check that. You've got time to do it. You want to make sure that this parts are correct for your formula. Then we just carry out the formula u times v. So we get 1/2 x squared sine 2x minus the integral of v du. So the 1/2 times 2 cancels out, leaving us with x times sine 2x dx. And if you notice here, while it has reduced, we still have a product. We still have a product. So it did simplify down, but not enough. So we need to do derivative or integration by parts a second time. So this time we'll have the x be the u. That way when you derive it, the x now simplifies out to just dx. So the sine 2x is our dv. And when we integrate it, we get a negative 1/2 cosine 2x. Remember, your sine, when you integrate it, becomes a negative cosine, and then you divide by the 2, which gives you your negative 1/2. Again, double check it by going forward. The derivative of cosine is a negative, sine 2x, so that negative times the negative 1/2 would make it positive, and then multiplied by the 2 would cancel the 1/2 to make it 1. So just really be careful with your positives and negatives and also your fractions to make sure that this is accurate. So the mechanics is very important. Details, the little fine points there, your plus and minus, all of those details, really be careful in that. Think it back and forth. Even if it takes you a minute on those, it's really important. The rest of this is algebra, it will work out. So now we move into the formula again. This part just carries down 1/2 x squared sine 2x. Now be careful here, because we did it twice, this negative has to distribute through this formula, okay? So we have a negative times uv. And since v is negative, this negative and this negative cancel to make positive. We get 1/2 x cosine 2x. There's no integral on that because of this right here. Then this negative also distributes to this negative to make it positive times v du, but then again the negative makes it negative. So you got 3 negatives, this one distributing through, this one in the formula, and this one on the v. So 3 negatives make a negative from 0 to pi fourths, and here we have 1/2 cosine 2x dx. Now it is simplified enough that we can actually integrate that. So we get 1/2 x squared sine 2x plus 1/2 x cosine 2x minus, and then when you integrate this, the integral of cosine 2x is sine 2x, divide by the 2 gives you 1/4. Now we're done with integrating. Now we can evaluate it from 0 to pi fourths. So when you plug in a 0, or when you plug in the pi fourths times 2 is pi halves. Sine of pi halves is 1. And when you plug in pi fourths in here and square it, you get pi squared over 16 times 1/2 is pi squared over 32. So don't forget to square even the pi, and you get your pi squared over 32. Pi fourths plug into here gives you pi halves. Cosine of pi halves is 0. So this cancels out. And pi fourths times 2 here is pi halves. Sine of pi halves is 1. So you get your minus 1/4. Top minus bottom, plug in a 0. Here's x. So all this is 0. Plug in a 0. All that's 0. Sine of 0 is also 0. So that's just this. So this becomes pi halves over 32 minus 1/4. And then we want to factor out the 1/32. and it leaves you with pi squared minus 8. When you take out the 32nd, 8 over 32 is 1/4. So you're factoring out that 1/32. Like, remember, it's dividing it. So if you invert and multiply, 32 divided by 4 is 8. So here is our final form. That is what we want. And so here is an example of integration by parts 2 times in order to work our way through it. I have one more example for us for this video. Okay, for our last example for this video, let's again go and look at where we're at. W19, paper 31, number 6, says by differentiating cosine x over sine x, show that if y equals cotangent x, then dy dx equals a negative cosecant squared x. Basically what they're doing is they've taken cotangent, turned it into a product. They're wanting you to use the product rule by differentiating to come up with the derivative as being a negative cosecant squared x. Actually, this is already in your formula sheet, that the derivative of cotangent is a negative cosecant squared x, but they're wanting you to change cotangent into the quotient and use the quotient rule to get the same thing. Now, this is important because remember, you cannot integrate, that is, you cannot go backwards unless you have a going forwards. So the fact that we get this cosecant squared going forwards means that we can go backwards. But again, it is in your formula sheet. So it says show, and this is the part that we want to do, show that the integral from pi halves or pi fourths to pi halves of x times cosecant squared x dx equals 1/4 times pi plus ln 4. Notice 6 points. So back to the board here. So I just put the result up here. Like I said, it is in your formula sheet. But in part 1, and because oftentimes Cambridge use these linked questions, it's always good to see what you did in the previous part. Y equals cotan x, and the derivative of that is a negative cosecant squared x. So what we want to do is show that the integral from pi fourths to pi halves of this x cosecant squared x dx equals this expression right here. And the important thing to us is, first of all, there's really nothing to simplify in this case, but it's always a good thing to ask ourselves, do we have to do anything to prepare it for integration? And the answer to that is no. So as we move into integration, we have to choose a method. And because this is a product of unlike terms here, we have an algebraic with a trigonometric, then we want to integrate by parts. So of course our x is a good candidate for the u, because when you take the du, it simplifies out, leaving us just the dx. So that means the cosecant squared x dx will be the dv. And that's important because you just did the derivative going forward, meaning now if we integrate, it's just going to go backwards. So it's going to give us the negative cotangent x, because now we're starting from a positive cosecant squared. So this negative has to transfer back, giving us a negative cotangent x. So this is the derivative by parts, or separating out the parts. Now we follow the formula, the u times v. U times v gives us a negative x cotangent x, plus the integral from pi fourths to pi halves of v du. And actually it's a minus in the formula, but because this is minus, those two minuses make a plus, and then we just get cotangent x dx. Now you look in your formula sheet and you don't find cotangent, and so at first you're like, what do you do now? Because it's not, cotangent is not the result going forward. You can derive cotangent going forward, but it is not the result of a derivative, so we cannot go backwards from it. However, if you remember, their hint in the first part was to make it a fraction, and cotangent as a fraction is cosine over sine. So writing it in that form, and if you remember our list of things that I showed you in the previous videos that you need to refresh your mind with, first of all, is it a basic formula? No, it's not in your formula sheet. The second thing is the top the derivative of the bottom? Well, what's the derivative of sine x? It's cosine x. So this is the form f prime of x over f of x. So we need to recognize this as actually being a logarithm. Okay, that's where that list of 6 things that I gave you in the previous videos helps you when you get stuck because you don't find it in the formula sheet. You need to go through that list so that you can, think through it. It's there somewhere. You just have to discover it. In this case, change it into its fraction form. Then you can recognize the top is the derivative of the bottom. So this is going to be a logarithm. So this part just carries down negative x cotangent x plus, and this is going to be the ln of f of x, which is the bottom one here. So we get ln of the absolute value of sine x. Again, you can check it by going backwards. The derivative of ln sine x is 1 over sine x. dx, the derivative being the inside, is the cosine x. So derivative going this way, integration going this way. So we double checked it works. Now we've done the integrate, we're ready to evaluate it from pi fourths to pi halves. We plug in the pi halves first, top minus bottom. And when we put pi halves into this, might be easier to put it into the fraction. Cosine of pi halves, same thing as cosine of 90, is 0. So since the top is 0, that wipes out this whole thing and becomes 0. Sine of pi halves is 1, but ln of 1 is also 0. If you need your calculator, you can use it, but some of this you should become familiar with in your mind, especially these quadrantal angles like that. Then top minus bottom, so we have our minus. Make sure you put the parentheses because later we have to distribute. Now we have pi fourths, and cotangent of pi fourths, if you have cosine of pi fourths, that's 1 over root 2. Sine of pi fourths is also 1 over root 2. So 1 over root 2 over 1 over root 2 is 1. And then you get 1 times the pi fourths, and it's negative. So a negative pi fourths. And then you plug in the pi fourths in here. You have 1 over root 2, so you have ln of 1 over root 2. Distribute your negative. This whole front part was 0 anyway. Distribute your negative, makes a positive pi fourths minus ln of, and now I change it to its exponent form. So it's 2, bring it 2 to the 1/2, bring it upstairs, makes it 2 to the negative 1/2. Now using our laws of logarithm, we can move that exponent to the front as a coefficient. So that becomes pi fourths plus 1/2 ln 2. And we factor out that 1/4, and you get pi plus 2 ln 2 when you divide out that 1/4. And then this 2 can go back up as the exponent and make it 1/4 pi plus ln 4, which is what they wanted up here. So these stages, probably right in here, going through here, there's probably a couple of different ways that you could do it. This is just the way that I did it. So there's probably more than one way to get to this answer. So it doesn't necessarily have to be this particular way, but that's the way that came to my mind when I did it. So there we've went through 4 different examples and seen several different cases of integration using the by parts that we had to do to be successful at the problem. Again, be very careful in setting this up. If those are correct and you follow the formula through carefully with these plus and minus signs, you should be pretty good. But if you mess up on establishing your parts, then of course that's going to carry through the rest of the problem. So as always, thank you for joining me in the Zoom room. Hope to see you again next time. And for now, I'll just say goodbye.